Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering a whole new topic called server-side request forgery, or in short, SSRF. Just like with the other theory videos, this is pretty much a brain dump of everything that I know about SSRF attacks, and so it's going to be a long one. But by the end of the video, you'll have all the fundamental knowledge that is required to complete the 7 hands-on lab exercises that we will be covering in the next upcoming videos. Alright, let's get started. The agenda for today is to first cover the technical details behind SSRF attacks. So what is an SSRF vulnerability? What are the different types of SSRF vulnerabilities? What are the conditions that must be satisfied for a page to be vulnerable to SSRF? How common are SSRF vulnerabilities, and so on. Next, we'll cover how to find SSRF vulnerabilities from both a white box and a black box perspective. So if you're given an application and possibly even the application source code, how would you approach testing the application in order to determine if it's vulnerable to SSRF? Once you've found that the application is vulnerable to SSRF, how do you exploit it in order to achieve your end goal? Then we'll end the presentation by covering the different techniques that you can use in order to prevent or mitigate SSRF attacks. Okay, let's get started with the first section, which is what is an SSRF vulnerability. Now, to better understand the vulnerability, we'll first take an example and then define what SSRF attacks are. Imagine you have a user and a shopping application. The application is hosted on an internal network that is protected by a firewall. The application itself is public-facing so that everyone on the internet can access the application and shop online. Now, this is a modern complex application that makes use of other services in order to implement certain functionalities. And these services can both be internal to the organization's network, like this service over here, or external to the organization's network, like this third-party cloud system over here. For security reasons, the only software that is allowed to communicate with these services is this application. So if a user tries to communicate directly to the third-party system or to any of the services that are hosted on the internal network, the connection will obviously be denied. So the important thing here to note is that there's a trust relationship between this application and any of the internal services. Similarly, there's a trust relationship between this application and the third-party cloud system. And in a bit, you'll understand why I'm spending quite a bit of time explaining this point, because it'll be very relevant in understanding why SSRF vulnerabilities work the way that they do. Alright, now let's talk about functional use cases of the application. Imagine you have a regular user that would like to buy a cupcake on the application. The first thing that the user has to do is check if this cupcake is in stock. And to do that, the user clicks on the Check Stock button. This initiates a request to the service that is responsible for checking if an item is in stock. Now, this request is a post request that sends the URL responsible for checking if an item is in stock as a parameter in the request. So in this scenario, the service that is responsible for checking if an item is in stock is called stock.shop.net, and it's hosted on port 8080. And it takes in a parameter called product ID that identifies the ID of the product that you want to check. Now, once the service obtains the request, it checks if an item is in stock and sends back a response to the application, which in this case is that there's 58 cupcakes left in the inventory. Alright, that's the first use case of the application. The second use case is once the user knows that an item is in stock, the next obvious step is to buy the item. So the user clicks on the buy button, which initiates a request to the third-party system that is responsible for managing the sales of products. In this case, the third-party system is AWS service.net. It's hosted on port 443 because it's HTTPS, and it takes in the product ID of the item that you want to buy. Now, once the third-party system obtains the request, it processes the request and sends back a response to the application confirming that the item was successfully purchased. Okay, so these are the two use cases of the application. So what could go wrong here? Now, imagine these URLs that the application is making in order to initiate requests are 1, user controllable, and 2, not properly validated by the backend. So what does that mean? When I say user controllable, that means the user or the client has the ability to change the URL on the client side before it's sent to these services. And when I say it's not properly validated at the backend, that means there are limited to no controls being applied in the backend code that reject the request that has been tampered with on the client side. So what that means is, one, I can tamper with this URL and change it to anything I want, and two, the application will accept that URL for me. Now, you're probably getting a hint for how you can exploit this vulnerability. Imagine instead of letting the application function the way it's supposed to, you intercept the request before it's sent to the service, and instead of asking the application to check if an item is in stock, you request the admin page of the application. So over here, what I did when I clicked on the check stock button, I intercepted the request with my burp proxy, and then instead of asking to check if an item is in stock, I asked for the admin page of this service over here. Now, since there's a trust relationship between this application and this application, the admin page of the internal application gets displayed to the attacker. So you could see over here, the admin page has view items, add items, and delete items. Now, as an attacker, you can't simply click on the button add items or delete items, because if you click on them in the application, it will view it as an external request, and the request will be denied by the application because there's a firewall that is protecting this application from any external requests. However, what you could do is right-click on any of these items, view source code, and find out what the URL is for adding an item or for deleting an item, and then re-exploit the SSRF vulnerability by sending the URL that deletes an item or adds an item to the service. And again, because there's a trust relationship between this application and this service over here, the service will process the request and delete the items that were specified in the request. And this is a classic example of how you could exploit SSRF vulnerabilities in order to gain access to sensitive functionalities in other applications. Another thing that you could do with SSRF vulnerabilities is you could port scan the network. So you can use the SSRF vulnerability in order to run an automated attack that scans the entire private IP range for servers that are running applications on, say, port 80 or port 443. And since both the application that is vulnerable and other applications that we're scanning are on the internal network, they can communicate with each other. And therefore, you could use the SSRF vulnerability in order to see which servers are up and what services are running on those servers. Of course, there are limitations to what you can do with that, and we'll talk more about that in the next section. In this case, we find out that there's a Cold Fusion application that is running on a server with IP address 10.2.1.172, and it's running on port 80. And we all know that previous versions of Cold Fusion have been known to be vulnerable to authentication bypass vulnerabilities. So depending on the version of the software that they're running, you might be able to re-exploit the SSRF vulnerability in order to bypass authentication on the server, or even worse, gain remote code execution on the server itself. And we'll see several examples of this in the lab videos where you actually gain hands-on experience exploiting SSRF vulnerabilities in order to port scan the internal network and look for vulnerable internal servers that could potentially allow you to gain remote code execution on the server itself and gain a foothold in the internal network. Alright, so that was example number 2. Another example for how to exploit SSRF vulnerabilities, and it'll be the last example for the day, I promise, is SSRF vulnerabilities that exist within applications that are hosted on the cloud. So in this scenario, it's running on the AWS platform, and depending on the permissions that the IAM role has, you might be able to gain remote code execution on the EC2 instance. And where have we seen that before? This has happened in a pretty famous breach that you've probably heard about called the Capital One breach that occurred in 2019. It was one of the biggest data breaches to ever occur, where a hacker gained access to more than 100 million Capital One customers' accounts and credit card applications. And the way that the attacker gained access to all this information is by exploiting an SSRF vulnerability in a cloud instance. So what the attacker did is the attacker used an SSRF vulnerability to obtain the metadata of the instance itself, found credentials for an IAM role that had excessive privileges, allowing the listing and access of S3 buckets. And so the attacker was able to list the buckets and download them locally. And that's pretty much how the attack worked. And this really begs the question, why did Capital One not catch this vulnerability before it went into production? A big organization such as Capital One should have multiple lines of defense, where if it's not caught by the first line, it gets caught by the second line, and if it's not caught by the second line, it gets caught by the third line, and so on. So if it wasn't caught by the developers, it should have been caught by the vulnerability scans. And if it wasn't caught by the vulnerability scans, it should have been caught by the vulnerability assessment. And if it wasn't caught by the vulnerability assessment, it should have been caught by the pen test. And so neglecting all these basic security practices caused a breach that not only damaged the reputation of Capital One, but caused the personal data of millions of its users to be exposed. And this really shows the detrimental effects of SSRF vulnerabilities. Alright, so we tried to explain SSRF vulnerabilities by using 3 examples. Now we're ready to define what an SSRF vulnerability is. SSRF is a vulnerability class that occurs when an application is fetching a remote resource without first validating the user-supplied input. This allows an attacker to coerce the server into making network connections on behalf of the attacker and potentially target systems that are behind firewalls. So if you see an application sending an IP address, a hostname, or a URL in a parameter, it definitely needs to be tested for SSRF because it could potentially be vulnerable. Alright, so we talked about what an SSRF vulnerability is. Now let's discuss the different types of SSRF vulnerabilities. There are 2 types of SSRF vulnerabilities. The first one is regular or in-band SSRF. This is where you as an attacker can tamper with a URL, and the response to the URL you requested will be displayed back to you in the application. So all the examples we saw in the previous slides were of type regular or in-band SSRF, where we requested, for example, the admin page, and then the content of the admin page was displayed back to us in the response of the application. So if you request a URL and then the content of the URL is displayed back to you as a response in the application, that means it falls under the regular or in-band SSRF category. The second type is called blind or out-of-band SSRF, and as the name suggests, this is where the application does not provide you back a response from your request. So in this scenario, if you were to request the admin page, the application might actually be vulnerable and the exploit was successful. However, the response is not displayed back to you in the application. So in this scenario, in order to prove that a vulnerability does really exist, you need to force the application to make a DNS or an HTTP request to an attacker-controlled server, let's say Burp Collaborator. And if you get the request on your server, that means that the application is vulnerable to SSRF. If you don't get the request, that means it's highly likely that the application is not vulnerable to SSRF. And this type of vulnerability is obviously much harder to exploit and show impact of, which is why we have 2 exercises in the next upcoming videos explaining how to prove that an application is vulnerable to blind server-side request forgery, and then how to use the vulnerability in order to port scan the network for any servers that are vulnerable to shell shock and exploit the shell shock vulnerability in order to gain remote code execution on the internal network. So this is a really fun exercise that we're going to go through in one of the lab videos. Alright, so these are the different types of SSRF vulnerabilities. Now let's talk about the impact of SSRF attacks. So we touched a bit on this when it came to the examples. So some of the examples showed us that we could perform sensitive functionality in other services that are hosted on the internal network. In other examples, we saw that you could gain remote code execution on the service itself. In other examples, we saw that you could port scan the network. And so that's why when it comes to describing the impact of SSRF attacks, I always say it depends on the functionality in the application that is being exploited. So it's very highly contextual. And what that means, it really depends on the context of the application that you're running with. So the application might be very restricted. And so all you can do is communicate with one service in the internal network, whereas in others, it might not be restricted at all. And so you could port scan the entire network and potentially find vulnerable servers and exploit those vulnerabilities in order to gain remote code execution on the internal server. And so when comparing it to CVSS scoring, I always consider the CIA triad: confidentiality, integrity, and availability. And for SSRF vulnerabilities, it really depends on each individual vulnerability. So all three of them, confidentiality, integrity, and availability, could be from none to all the way to high, depending on the vulnerability you're exploiting. But if we're talking about impact of SSRF attacks, it could lead to a denial of service attack. It could also lead to sensitive information disclosure or scanning of the internal network or compromise of internal services, and in worst case scenarios, remote code execution. So it really depends on each individual application and each individual SSRF vulnerability that you're exploiting. All right, so we talked about the impact of SSRF vulnerabilities. Now the question is, how common and how critical are SSRF vulnerabilities? One way to measure that, and it's not bulletproof, is the OWASP Top 10 list. So for those of you that have not heard of the OWASP Top 10 project, it's essentially the list of top 10 most critical security risks in web applications today. It's updated every couple of years, so you can see we've got a list from 2013, and then we've got a list from 2017, and we've got a list from 2021, which came out only a couple of weeks ago. And as you can see in the 2021 list, server-side request forgery, or SSRF, is the 10th most critical security risk to web applications today. And this vulnerability was added from the top 10 community survey. So the community felt it was a vulnerability that was relevant and that could potentially have a high impact, and so it was added to the list, and we saw several examples of that in the past couple of slides that support that claim. So you definitely need to test for it if you do have an application that is fetching remote resources and communicating with other services. All right, in the past couple of slides, we discussed what SSRF vulnerabilities are, the different types of SSRF vulnerabilities, the impact of SSRF vulnerabilities, and how common and critical SSRF vulnerabilities can be. In this section, we'll move on and discuss how to find SSRF vulnerabilities. So imagine you've been given an application and asked to test it. How would you go about testing this application to see if it's vulnerable to any server-side request forgery or SSRF vulnerabilities? Okay, before we cover that, it's worth mentioning that the methodology used for finding SSRF vulnerabilities differs from one person to another person and is usually developed by experience. So just because I give you my methodology doesn't mean that you have to follow it to the letter. Instead, I would recommend that you take what is useful for you from it and then build an add-on to your own methodology as you gain more and more experience pen testing web applications. And like I say in all my theory videos, this statement applies to finding all vulnerabilities, not just SSRF vulnerabilities. Alright, so I've decided to split this into two categories depending on the perspective of testing, and the two categories are black box testing and white box testing. For those of you that have never heard of these terms before, black box web application pen testing is when the tester is given little to no information about the system. Usually the only information that the tester has access to is the URL of the application and the scope of the engagement. Whereas for white box web application pen testing, it's the complete opposite. The tester would be given complete access to the system, including access to the source code of the application. Now, there's a third category that I haven't included on the slide, and it's called gray box web application pen testing. This is a combination of white box and black box pen testing, where the tester is given limited information and access to the system. So for example, instead of just giving the tester a URL of the application, the tester is also given accounts to the application, and those accounts could be of different access levels to the application. So when it comes to my methodology of finding SSRF vulnerabilities, I loop both gray box and black box pen testing into one category, and that's because my methodology is the same regardless of whether it was black box or gray box pen testing. Because if I'm approaching it from a black box perspective, the only difference would be that my scope will be much more limited than the gray box perspective, unless I find an authentication bypass vulnerability. Nevertheless, the methodology of testing for SSRF vulnerabilities in public or private or authenticated pages is still the same, and that's why they're always looped in together. Now for white box testing, that's a category on its own because you actually gain access to the code and you need to learn how to review the code in order to find vulnerabilities, and so it's a category on its own. Alright, let's start off by talking about how to test applications from a black box perspective. The first thing that I do when testing an application is map the application. And what that means is I literally visit the URL of the application, walk through all the pages that are accessible to me within the user context that I'm running as, make note of all the input vectors that potentially talk to the backend, understand how the application functions, try to figure out the logic of the application, and so on. And while I do that, I have my burp proxy listening silently and intercepting all the requests that I'm making to the application. I would personally argue that this step is probably the most important step when it comes to testing an application, so make sure to spend quite a bit of time on this step before moving on to the other steps. Alright, so once I've mapped the application and I've listed all the input vectors or request parameters, I filter those input vectors on ones that contain host names, IP addresses, or full-on URLs, because that means that these parameters are being used to communicate with an external system and so could be potentially vulnerable to SSRF. Once I've mapped all my request parameters that are of interest to me, then it's just a matter of fuzzing the application with SSRF payloads. So what fuzzing means is you modify its value to specify an alternative resource and observe how the application responds. So depending on how the application responds, you might need to fine-tune your payload, and that's where SSRF defenses come into play. So if there's a defense in place, you need to attempt to circumvent it using known techniques. So if it's a blacklist, there are a ton of payloads that you can find online in order to circumvent blacklists. If it's a whitelist, you might be able to abuse how the URL parser parses the URL itself. And so depending on the defense that is put in place, you might be able to circumvent it. And that's how you would test for regular or in-band SSRF. Now you can't forget about blind or out-of-band SSRF. And so to test for that, for each request parameter, you need to modify its value to a server on the internet that you control. So think of burp collaborator, and monitor the server for incoming requests. If you get a request on your server, that means it's vulnerable to blind-based SSRF or out-of-band SSRF. If you don't get a request, that doesn't necessarily mean that it's not vulnerable. What you need to do is monitor the time taken for the application to respond, because the application might not be able to communicate with your server due to firewall rules. So the time taken for it to send back a response to your server might be slightly different if the resource itself doesn't exist, and you might be able to use that to prove that an SSRF vulnerability exists and then to achieve your end goal with the SSRF vulnerability. And that's pretty much how you would test for SSRF vulnerabilities from a black box perspective. Alright, let's move on to the white box testing perspective. So that's where you're given the source code of the application. The first thing that you need to do is review the source code and identify all request parameters that accept URLs. Like I said in the past couple of slides, this could be done by combining both a black box and a white box testing perspective. So personally, what I do is I still map the application from a black box perspective, and I make note of all the request parameters that taken URLs or host names or IP addresses, and then I search for those URL parameter names or function names in the code itself. And then once I find it in the code, I review the function in order to see if there are any defenses that are being put in place in order to mitigate SSRF vulnerabilities. And if it's a blacklist, it usually can be bypassed really easily. However, if it's a whitelist, what I usually do is I try to determine what URL parser is being used to parse the URL. And depending on the URL parser, you might be able to exploit it in order to bypass that defense. There's a really good talk by Orange Desai called A New Era of SSRF, Exploiting URL Parsers in Trending Programming Languages, that talks about how different URL parsers parse URLs differently. So a URL that might be invalid for a certain Python URL parser might be valid for another Python URL parser or another Java URL parser. And so depending on the URL parser that is being used in the code, you might be able to bypass it in order to send in your malicious payload. And we'll talk more about that in the next section when we discuss exploitation of SSRF vulnerabilities. Now, the nice thing about white box pen testing is you actually have access to the code, and so you don't need to do this guesswork that you do when it comes to black box testing, when it comes to, finding out what the URL parser is, finding out what the defenses being put in place are, and so on. In this scenario, you just look at the function that is taking in the URL parameter, you find out what URL parser is being used, you find out what defenses are being used, and then you attempt to bypass them. And if you think it might be vulnerable to SSRF, then you test any potential SSRF vulnerabilities in order to confirm that this parameter is really vulnerable to an SSRF vulnerability. And that's pretty much how I would do it from a white box testing perspective. Alright, so far we've learned the theory behind SSRF vulnerabilities and how to find SSRF vulnerabilities from both a black box and a white box perspective. The next thing we're going to discuss is how to exploit SSRF vulnerabilities. And that really depends on the type of SSRF vulnerability that you're dealing with. So in this section, we're going to cover how to exploit both regular or in-band SSRF and blind or out-of-band SSRF. And we'll start with regular or in-band SSRF. Imagine you've got a shopping application similar to the one we saw in the past couple of slides. In this shopping application, you can check if an item is in stock by clicking on the Check Stock button. And that initiates a request to the page /product/stock, which takes in the parameter stock API that contains the URL of the application that is responsible for checking if an item is in stock. So in this case, the application is stock.weliketoshop.net and it's hosted on port 8080. It takes in the path /product/stock/check, and it seems like it takes in two URL parameters, product ID and store ID. Now, once the application receives this request, it processes the request and it provides back a response with the number of items that are available in stock. In this case, it's 506. Now notice that the response to the URL is displayed back to us in the application, and that's why this classifies as a regular or an in-band SSRF vulnerability. Now, this type of vulnerability is so much easier to exploit than blind-based SSRF because you could simply request the URL that you want and the response will be displayed back to you from the application. So in this scenario, I'm requesting localhost/admin. If there is an application that is hosted on the loopback interface, so on IP address 127.0.0.1, and it has an admin page, it should be displayed back to me. So the response of the application is as follows. So I click on render in burp and it renders the response for me. And you could see over here, there's an admin panel and you have the ability to delete users. And so we can use that SSRF vulnerability in order to delete the users of the system. Now, the reason that this admin page was not accessible externally but is accessible on the loopback interface is probably because when the admins or the developers set it up, they assumed that only the person that authenticates to the server can access the application that is hosted on localhost. And that's why they didn't require authentication in order to access the admin page. However, with an SSRF vulnerability, if this vulnerable application is hosted on the same server as this application over here, which is hosted on localhost, that means you could use the SSRF vulnerability in order to access the application that is hosted on localhost. And that's what we did over here. Now, this is a really simple use case of SSRF vulnerabilities, and it doesn't always work, which is why when I'm describing how to exploit regular or in-band SSRF, I always divide it into two sections. The first one is if the application allows for user-supplied arbitrary URLs. So when we say arbitrary, that means you could request any URL you want. In this scenario, it's the easiest because the first thing you do is determine if a port number can be specified. And if it can be specified, then you just attempt to port scan the internal network using Burp Intruder. And we have a lab dedicated to doing just that, where we scan the internal network to look for other applications that could potentially give us access to sensitive functionality that is not normally available to an external user. Next, you could attempt to connect to other services on the loopback address, just like we did with the example, which is when we requested the application that is hosted on localhost, and that application happens to have an admin page, and so we requested the admin page and we were able to delete users. Now, this is in the best case scenario where there are no defense mechanisms put in place and you could request any arbitrary URL you want. Now, the second scenario, which is a little bit harder, is if the application does not allow for arbitrary user-supplied URLs. What that means is there are defenses put in place that will prevent you from requesting any URL you want. And when there are defenses in place, you need to try to bypass these defenses. And there are some known techniques that are used when it comes to bypassing SSRF defenses. One of them is to use different encoding schemes. So to obfuscate your URL by using a different encoding scheme. And this is usually used to bypass blacklists. So if the application has a defense mechanism that blacklists internal IP addresses, then you could use this technique over here in order to bypass that defense. So instead of using 127.0.0.1, which is contained in the blacklist, and so your request would automatically be rejected, what you could do is you could try the decimal encoded version of localhost, which is 21.30.76.4.33. So in this scenario, when you request http:// this number over here, it'll resolve to localhost, and this way you've bypassed the blacklist and you were able to access the application on localhost. There's another lab that is dedicated specifically to bypassing blacklist defenses, and we'll see that in one of the videos. Another thing that you could use is instead of using the entire IP address for localhost, you could just simply put in 127.1. Since the blacklist defense compares exactly on this string over here, this string will pass, and the reason this resolves to 127.0.0.1 is because the two octets in the middle automatically get filled with 0. So it'll resolve to the localhost IP address. Another thing that you could do is use the octo representation of localhost, which is 0177, a bunch of zeros, and then a 1. So if you use the URL http:// and this number over here, it resolves to localhost and you bypass the blacklist defense. And this is why you should definitely not use blacklists in order to defend or mitigate SSRF vulnerabilities, because there's a ton of ways on how you could bypass these blacklists, and this is just a few examples of them. Now, applications might try to avoid the limitation of blacklisting techniques and instead rely on libraries to disallow the calling of URLs that have a private IP address. And this is to prevent an attacker from port scanning the internal network. So one way to bypass that defense is to use something called DNS rebind attack. And the way you do that is you register a domain name that resolves to an internal IP address. So what happens is the application will have some kind of check in the code that checks what the IP address for this domain is. If it's an internal IP address, then reject the request. If it's not an internal IP address, then continue with the rest of the code. And what happens with a DNS rebind attack is when it's checking if this domain has an internal IP address, it requests the IP address of the domain. The DNS server responds back with an external IP address, and so the check passes. And then the second time it requests the IP address for that domain, it resolves to an internal IP address like 127.0.0.1 or whatever internal address that is relevant to your network. And this way you bypass that defense. Another bypass mechanism is called HTTP redirection bypass. In this bypass method, you use a URL that points to a server you control. This server has a public IP address, and once the URL is requested or visited, it redirects the vulnerable server to make a request to an internal service, and so you bypass the defense mechanism. And that's why you shouldn't allow HTTP redirect when it comes to processing URLs, and we'll talk more about that in the defense section of this video. Alright, last but not least is to exploit inconsistencies in URL parsing. We touched upon that in the past couple of slides. So I mentioned Orange Desai's talk called A New Era of SSRF, exploiting URL parsers in trending programming languages. I've got the link to the videos in the slides and the link to the slides in the description of this video, so make sure to check it out. The talk discusses how different URL parsers, even under the same language, parse URLs differently. So you've got the URL lib2 library parses URLs different from the request library, and then you've got the request library parsing URLs differently from the URL lib library, and so on. And so what you could do is you could exploit these inconsistencies in order to bypass SSRF whitelist defenses. I'm not going to spend much time on this in this video because we do have a whole dedicated video and a lab with hands-on experience where we exploit the URL parser in order to bypass the whitelist defense for SSRF vulnerabilities. So make sure to watch that video if you'd like to gain hands-on experience in exploiting URL parsers. Alright, so we talked about how to exploit regular or in-band SSRF vulnerabilities. Now let's discuss how to exploit blind or out-of-band SSRF vulnerabilities. Now, as mentioned in the previous slides, this vulnerability is called blind because the response to the URL you requested is not displayed back to you in the application. And so just by definition of how this exploit works, what you need to do is attempt to trigger an HTTP request or a DNS request to an external server that you control. So think of Burp Collaborator, and then monitor that external server to see if there were any network connections from the vulnerable server. So you need to force the application to make a DNS or an HTTP request to a server that you control. And if you receive an interaction, that means it's vulnerable. If you don't receive the interaction, that means it might not be vulnerable. Now, there might be defenses put in place when it comes to blind or out-of-band SSRF. However, you could use the same techniques that were mentioned in the previous slides to obfuscate the external malicious domain. So I won't go through them again for this slide. It's the exact same techniques that you could use when it comes to regular or in-band SSRF. Now, once you've proved that the application is vulnerable to blind SSRF, you need to determine what your end goal is. So if you've received a ping back to the domain that you control, that means it's vulnerable to SSRF. However, you need to show impact of your SSRF vulnerability. And an example of how to do that is you probe for other vulnerabilities on the server itself or other backend systems. So there's a specific lab video that is dedicated to blind SSRF, and I mentioned that in the past couple of slides. In this video, we'll exploit a blind SSRF vulnerability in order to port scan the network and look for applications that are vulnerable to shell shock. Once we find that an application is vulnerable to shell shock, we exploit the vulnerability in order to gain a foothold in the network or to gain remote code execution on the network. So make sure to catch that video if you'd like to gain experience in exploiting blind or out-of-band SSRF vulnerabilities and actually show impact of the vulnerability itself. Alright, there's a really nice extension in Burp called Collaborator Everywhere that is created by James Kettle. It automates the discovery phase of blind SSRF vulnerabilities or other blind vulnerabilities. And the way it works is you put the application you're testing in scope, and while you're mapping the application by visiting different pages in the application, what this extension is going to do, it's going to inject non-invasive headers that are designed so that they reveal if an application is vulnerable to blind vulnerabilities, such as blind SSRF vulnerabilities. So it'll do that manual check for you where you put in the domain of your Burp Collaborator, and then if you get a ping back, that means it's vulnerable. If you don't get a ping back, that means it's not vulnerable. It'll automate that portion for you so that you don't have to manually do it for every parameter. I also wanted to highlight an article that is written by the same guy that created that extension, so James Kettle. The article is called Cracking the Lens, Targeting HTTP's Hidden Attack Surface, and it talks about finding a bunch of vulnerabilities, including a blind SSRF vulnerability in a real-world scenario, and chaining it with other vulnerabilities in order to achieve your end goal. So this is a really, really good example of a real-life scenario of finding an SSRF vulnerability and then using it in order to show impact of the vulnerability. All right, we can't end this section without talking about automated exploitation tools, so web application vulnerability scanners. For those of you that have never heard of web application vulnerability scanners, they are essentially automated tools that crawl your web application and look for vulnerabilities. There's open source tools, there's free tools, and there's paid tools, and I've got examples of each category on the slide. Some of them cost nothing, others cost a couple of $100s, and others cost tens of thousands of dollars. I personally use either Zap or Burp, and I prefer Burp over Zap. However, I thought it would be worth mentioning that when it comes to finding SSRF vulnerabilities, you can always use web application vulnerability scanners in order to find the vulnerabilities. You shouldn't depend completely on a scanner. However, it does aid in the testing phase when it comes to identifying vulnerabilities in an application. So what I usually do is when I'm mapping the application by manually visiting every page in the application, I have my Burp proxy intercepting all the requests, and then I scan all these requests in order to find the low-hanging fruits. And then I depend on myself to do manual testing in order to find any other vulnerabilities that the scanner might have missed. And that wraps up our section of how to exploit SSRF vulnerabilities. Alright, we've reached the last section of this video, which is how to prevent SSRF vulnerabilities. Now, when it comes to mitigating SSRF vulnerabilities, I always like to use a defense in-depth approach, which is if one defense fails, the other defense is put in place to either prevent the attack from happening or at least reduce the risk of the attack if it does happen. And so we'll discuss two types of defenses. The first one is application layer defenses and network layer defenses that are used to prevent or mitigate SSRF vulnerabilities. And we'll start off with the application layer defenses. The first defense that you should use for all types of vulnerabilities, not just SSRF, is you should always sanitize and validate all client-supplied input data. So anything that is coming from the client side is automatically untrusted, and that's why it should always be sanitized and validated regardless of what vulnerability you're trying to prevent. The second defense is to enforce the URL schema, port, and destination with a positive allow list, or what is known as a whitelist. So ensure the set of URLs that are expected for the application to call are all available in a whitelist, and anything that is called beyond the whitelist should be automatically rejected. So if the application is supposed to call another application called weliketoshop.com, that application URL should be put in that whitelist. And every time an application requests for a URL, it checks if it's equal to what is in the whitelist. If it is, then the request goes through. If it's not, then the request should be rejected automatically. Next, you should not send raw responses to the clients. So remember in one of the examples, we requested localhost/admin, and then the admin page was automatically displayed to us. So that's a raw response. Instead, what you should do is you should send a custom response with what is expected from this page itself. So if the page is expected to display the number of items that are left in stock, then it should only be displaying a single field, which is the number of items that are left in stock, and not the raw response of the application. Last but not least, you should disable HTTP redirections, and this helps prevent against the HTTP redirections bypass attack that we talked about in the last section. Now, it's really important to note that you should never mitigate SSRF vulnerabilities by using deny lists, or what is known as blacklists, or regular expressions, because we saw in the past couple of slides how you could bypass blacklists by using things like the octal representations of IP addresses or the decimal encoding of IP addresses or so on. And there's a ton of bypasses out there that are available for anyone to use, and that's why you should never mitigate SSRF vulnerabilities by using deny lists or blacklists. Alright, that was the application layer defenses. Now let's discuss network layer defenses. The first one is you should segment remote resource access functionality in separate networks to reduce the impact of SSRF. So this doesn't fix the SSRF vulnerability itself. You could still exploit it and show your proof of concept. However, you can't show impact of the SSRF vulnerability. So if the server is sitting by itself on its own network and is segmented from the entire network, that means you can't call anything in the entire network. So you could attempt to port scan the network, however, your request will always be denied because the firewall is blocking your connection from accessing any other server on the internal network. So this mitigates SSRF vulnerabilities in a sense that you can't use that SSRF vulnerability in order to cause any detrimental impact. The second one is to enforce deny by default firewall policies or network access control rules to block all but essential intranet traffic. So this one is pretty self-explanatory. Make sure that the server that has this functionality has limited access to intranet traffic, and that's done by configuring firewall policies to prevent the connection to internal services. All right, and that concludes the network layer defenses. So we're at the end of the video. I've put up some resources on the slides in case you want to learn more about SSRF vulnerabilities. The first one is the Web Security Academy SSRF section, which is what these slides are based on. The second one is the Web Applications Hackers Handbook, chapter number 10, Attacking Backend Components, pages 390 to 392. It covers SSRF attacks. The next three resources are OWASP resources that discuss what SSRF vulnerabilities are, the different SSRF payloads that you could use, and then how to prevent SSRF attacks. And then you've got another resource from Sec Labs, which talks about how to prevent SSRF vulnerabilities. And last but not least, we've got Orange to Size talk on how to exploit URL parsers in order to bypass SSRF defenses. And that concludes our video. In the next upcoming videos, we'll gain some hands-on experience in exploiting SSRF vulnerabilities and bypassing SSRF defenses.